So the last talk of this session is by Shahrzad Zare about Young-Mills Glueballs versus closed bosonic strings.
Thank you. Good morning. I'm glad to have the opportunity to talk about our work with Sergei Dubovsky and Guzman Hernandez today. So in the quest of following the quest of a weakly coupled string description of SU and Yang-Mills, which is in a good agreement with Lattice data, I'm going to discuss and compare two approaches in 2+1 and 3+1 dimensions. But before that, let me quickly mention what are the observables that I'm going to mention in this talk. So in lattice simulation, an IR regulator is defined by compactifying one of the special dimensions. Then there will be two sectors, one associated to pairs like C, which bind around the compactified dimension, defining excitations around a flux tube, and the other one, the contractible pairs like C prime, defining glue ball masses and quantum numbers, J spin, PC, P parity, and charge conjugate. These two sectors are decoupled in large n limits, so I can safely say that I am going to focus on the second sector. So these two approaches that I'm going to, these are the two approaches I'm going to discuss. The approaches to the string description of Glueballs, which is closed folded string, axionic string and set or ASA, and effective closed string. So in ASA, one can imagine two open strings which are attached at, which are glued at the endpoints. In effective closed string, one directly works with closed string language. So basically, we are expanding around a classical solution, which is a rotating rod with large spin. And the calculation I'm going to show are up to leading order in 1/J expansion. So ASA makes two assumptions. The first one is that the Hilbert space of Glueballs could be built by summing over the string levels, and at each level, the Hilbert space is equal to the tensor product of left moving and right moving excitations. And the second assumption is that the Hilbert space of left moving and right moving are same as the Hilbert space of an open string. Well, I emphasize that I'm talking about 3D here because in higher dimension, we could have additional degrees of freedom on the worksheet. So in both approaches, one could start from non-Boguta action or equivalently Polyakov. As we are working in uncritical dimension, we have to add Pochinski-Strominger term. But well, these terms, which these dots mean the higher order operators, and along with the Pochinski-Strominger action, they won't contribute to the leading order calculation. And now I think it's a good time that I mention what the axionic is referring to in the axionic string handsets. It's actually referring to the 4D dimension where there is an additional massive degree of freedom on the worksheet, the worksheet axiom. And the contribution of this axiom to the action is shown by these added terms. Here, mass M is the mass of the axion, and SA is the coupling term, which again doesn't contribute to the leading order calculation. So I have to skip the details of calculation because of time, but the result of calculation for a spectrum in ASA gives us the spectrum for open string. Then using tensor square structure, which was one of the assumptions of ASA, one can get the mass and spin of the Glueballs set by summing over the masses and spin. So here we will have a tower of oscillators, and each of these oscillators increase the level, the energy level by an integer n+1, which is the frequency of the oscillator. So it starts from 2. In effective closed string, on the other hand, we can directly get the spectrum for closed string for the Glueballs states. So we will have 2 towers of oscillators. But here, the states built by these operators are not all physical, because some of them are not invariant on their Z2 transformation, sigma plus pi. So we have to project out those states. So here I'm showing some numerical examples. So in ASA, we can calculate the multiplicity of each level. Then the square of those numbers will be the multiplicity of Glueballs states, Glueballs states. In effective closed string, on the other hand, we can directly get the multiplicities of Glueball, but you can see that already in the second level, there is a mismatch. I am going to momentarily tell you which one matches better with the lattice data. But before that, let me quickly generalize this to higher dimensions. But in higher dimensions, I am going to focus on effective closed string because at each dimension, the modifications for tensor square structure in ASA gets complicated. And also we will have this additional massive degrees of freedom. But in effective closed string, again, we will have terms due to possible additional degrees of freedom. Other than that, we will have new towers of oscillators. This time the frequencies n, so starting from 1. And we will need to Z2 projection. Specifically in 4 dimension, we will have have to add the axion to our process. So there will be some axionic terms and 2 towers of oscillators, but one should be careful about Z2 projection, because axion carries Z2 symmetry charge. So, or sorry, charge is charge under Z2 symmetry. So one should be careful about the states which should be projected on, and the states should be kept. So here it's the numerical results for the multiplicities of Glueballs states predicted by these 2 approaches. The red entries are the regions that these 2 approach match. So basically at each level, for the sectors with spin between n and 2n, they coincide. But effective closed string starts to count more states. And here I wrote it overcount because it's actually the ASA, which is in a better agreement with lattice data. So here you can see the lattice data, and ASA distinguish each of the energy levels. So each of these colors show one level, and so you can see that the multiplicities match between data and the ASA predictions. But as I said already, at the second level, for example, here, effective closed string predicts 5 states, but we only have 3 states, as ASA also predicts. So ASA, other than multiplicities, could give us the parity assignments. So due to this tensor square structure, there will be 2 predictions. One is that the states on ready trajectory, will have even spin, and the other one is that the odd spin states come in pairs of opposites, C parity, because they may only appear in decomposition of product of different spins. And it's exactly what we can see in the lattice data. So the states on the ready trajectory have even spins, and the states with odd spin come in pair. Finally, I can show the, all the discussion about 4D is an ongoing research, but I can show some of the comparison between some of our predictions and the lattice data. So the states shown by violet circle are string states. You can see that there are additional states which are candidates for axionic state. We calculated their parity assignment and saw that they actually match with the parities of these states. However, for example, in spin 2, each of these could be either like string states, let's say of some higher level string states, or axionic states. Also, we predicted more states here. So I guess having more lattice data and like heavier states could help us to evaluate these predictions better. So to summarize, two weakly coupled string descriptions of SU and Yang-Mills, 3D and 4D glueballs. In large n limits, ASA predicts that there is an additional degree of freedom in 4D. Both of these approaches match in the vicinity of leading ridge trajectory. Effective closed string overcounts the states. It's ASA, which is better, which is in better agreement with lattice data. ASA helps us to do C and P parity assignment. Effective closed string help us to do calculation for 4D and like add the axiom. But we predicted more states in 4D compared to lattice data. So as a future plan, if we can have more lattice data, we can evaluate better our predictions. And we are also working on higher order calculations to, for example, explain the mass splittings. But when one goes to higher order, should be careful about the effect of the folds. So one of the future directions could be finding an effective theory close to the singularities in the worksheet due to the folds. Thank you for your time and attention.
Thank you for the excellent talk.
Can we think of these different ansatz as coming from imposing different boundary conditions at the folds for the modes on the string?
No, it's not about the boundary condition, and it's mostly about like this language. In effective closed string, we do have a closed string, but in ASA, we do our calculation for an open string. Then we use a tensor square structure and a level matching condition to find the glueball states.
There is an interpretation for why you see too many states in this closed string approach? I mean, do you understand what additional criteria you would have to impose to get it to the right set of states?
No, that's a great question. Maybe one should ask what is the special thing which happens when J is equal to N, where these two approaches don't match. But I don't have a good answer for this.
We did this exercise because one can also compare in the critical case where we know the full spectrum and compare that to kind of this effective calculation. And the effective string theory calculation also overcounts because kind of state on the leading edge trajectory, you can think of some condensate of some number of oscillators. And when you consider excitation level equal to the number of state in the condensate, like when you go above that, then effective field theory overcounts. So that's by itself, it's not too surprising that effective theory overcounts. It's surprising that this ASA calculation that seems to get it right compared. Actually doesn't get it, for instance, in critical dimension, the similar strategy wouldn't get it right because it would also overcount at the open string level. But somehow comparing to actual in 3D, comparing to global data, it seems to miraculously produce.
But if I understood correctly, it doesn't quite match in 4D. I mean, you said better agreement, but not perfect agreement, right? I mean, wasn't there some additional state, or did I misunderstand?
Well,
No, actually, I didn't show the numerical results for 4D, but in 4D also we will have this region that they match. And I didn't have time to explain ASA in four dimension, but
also
yes.
in 4 dimensions, we don't really know yet how to do full, like, because there is additional massive state
I see.
And was it like, that's why we're using closed effective strings. That's clear how to include it. But in this tensor structure calculation, yeah, we don't know what's the correct specification. So when you say the degrees, it really in 3D, it works surprisingly well, but in 4D, that's kind of work in progress to understand.
Just one general question is, so in in holographic examples, we have this warped fifth dimension, and there definitely we see in those models the excitation associated with that. Do you see any sign of that in any of these global spectra?
Not sure. No.
So,
For sure, not in 3D. In 3D, there's no wrong way.
okay. All right, let's thank Shahrzad.